Welcome to This Explainer. Today, we're zeroing in on one absolutely fundamental, game-changing concept: how inertia keeps objects moving. You experience motion every single day of your life, but I guarantee that by the end of our time together, you are going to see the physical world in an entirely different light.
So let's kick things off with a quick question. Think about it. If you slide a book across your desk, or if you just stop pedaling your bike, you eventually come to a stop, right? Our everyday experience tells us that things just naturally want to rest. But is that actually the default state of the universe? Or is there some invisible trick being played on us?
Section 1. The myth of stopping. To really understand motion, we actually have to jump back over 2,000 years to the Greek philosopher Aristotle. He believed, incorrectly as it turns out, that a constant force was required to keep a moving object at a steady speed. And honestly, it makes total intuitive sense, right? If you want to push a heavy box across the floor, you literally have to keep pushing it. The second you stop, the box stops. So for over 2 millennia, pretty much everyone just accepted that motion requires constant pushing.
Moving on to Section 2, Galileo's ramp revelation.
Fast forward to the late 16th century. Galileo steps up and challenges Aristotle with this brilliant thought experiment. I want you to imagine a perfectly smooth, U-shaped ramp. Galileo realized that if you drop a ball down one side, it's going to roll down, cross the bottom, and roll right up the opposite side. And ideally, it tries to reach the exact same height on the other side that it was dropped from. Now, in the real world, it only almost reaches that exact height, due to a little thing we'll talk about in a minute. But Galileo asked, what if the ramp was perfectly smooth? And then he mentally altered the ramp. If you lower the angle of that second half, the ball suddenly has to travel further and further along the track just to try and reach its original drop height. But what happens if you take that second half of the ramp and just lay it completely flat? The answer is honestly kind of mind-bending. If we flatten the end of that track and remove friction entirely, Galileo realized the ball would move continuously at a constant speed in a straight line forever. It would just keep rolling into infinity, desperately trying to reach a height it can literally never achieve on a flat surface. This proved you don't actually need a force to keep an object moving. If nothing gets in its way, motion is its natural, perpetual state. Which brings us to Section 3, the friction factor. So, if things are supposedly built to move forever without a push, what exactly did Aristotle miss? Well, friction. But we need to be incredibly precise here. Friction isn't just a force that opposes motion. Why? Because friction actually enables motion too. Think about it. Without friction between your shoes and the ground, you wouldn't even be able to walk. Instead, we need to understand that friction is a force that opposes sliding between two surfaces, and it's totally influenced by how rough those surfaces are. Check out this side-by-side comparison from our physics simulation. On the left, we've got a box gliding beautifully at a speed of 40 meters per second. Notice the applied force there? It's a big, fat 0 newtons. Nobody is pushing it, yet it's gliding flawlessly because there is 0 net force acting on it. Now, on the right, we introduce a rough surface. Suddenly, even if you were pushing it, the very moment you let go, it's that friction force, not some magical lack of pushing, that alters its speed and drags it to a halt. Friction is the real thief of continuous motion in our daily lives. Once we bust that friction myth, we arrive at this massive, foundational scientific reality: inertia. This is the inherent property of an object to resist changes in its motion. Whether it's sitting perfectly still or moving uniformly in a straight line, it just wants to keep doing exactly that, unless an external unbalanced force comes along and forces it to change.
Let's dive into Section 4, Unstoppable Inertia in Motion.
Let's put this universal rule to the test with something we call the crash test can experiment. Place an empty can on a skateboard. When you yank that skateboard forward abruptly, what happens? The can tumbles backward. It's as if it was left behind. That right there is inertia at rest. The can wants to stay still. But the second part is even cooler. Once you get the skateboard moving steadily, the can is moving right along with it. If you crash that skateboard into a wall and stop it abruptly, the can doesn't stop. It keeps flying forward. That is inertia in motion. The skateboard experienced a stopping force, but the can didn't, so it just kept on going. We also see this perfectly illustrated in circular motion. Picture spinning a marble inside a circular ring on a table. The marble is forced into a circular path because the ring keeps pushing against it. This is what we call centripetal force.
But if you suddenly lift that ring away and remove the boundary, the marble doesn't keep curving. Its inertia dictates that it must travel in a perfectly straight line at a constant velocity from the exact split second the ring is removed. So, as you can see, an object's state of motion only ever changes when a net force acts upon it. Otherwise, it simply resists any change. Inertia at rest means stubborn stillness. Inertia in motion means unstoppable forward momentum. They are literally two sides of the exact same physical law. Without a net force to intervene, objects are trapped in whatever state they happen to be in.
Finally, Section 5, Real-World Inertia Applications. Why does this invisible rule actually matter to you outside of a physics lab? Well, because it governs almost every single action you take. Understanding inertia transitions from a fun science fact to practical, life-saving knowledge. Ever noticed it's way easier to balance on a bicycle that's moving than one that's sitting still? Inertia at work. Or when you pull wet clothes from the wash and give them a sharp jerk to snap the water out. You're pulling the fabric quickly, but the water droplets have inertia. They want to stay exactly where they were, so they separate from the accelerating fabric. But most importantly, think about road safety. When your car is traveling at 60 miles per hour, your body is also traveling at 60 miles per hour. If the car hits something and stops instantly, your body's inertia means you will continue moving at 60 miles per hour. That is exactly why seatbelts and airbags are absolutely crucial. They provide the necessary external force to change your body's state of motion safely. I want to leave you with this provocative thought about your own inertia today, and I hope it fundamentally shifts how you experience every single movement you make from here on out. The universe doesn't inherently want things to stop. It wants things to keep doing whatever they're already doing. So, the next time you hit the brakes in your car, or slide into home plate, or even just stop walking, take a moment to realize you are fighting a battle against the fundamental rules of the cosmos. Thanks so much for joining me on this explainer.